Hi, welcome to Pre-Calculus. Today we have a discussion about a polar equation named Limacon. That's French for a snail. Let's go take a look at this graph first, see what is it that we are going to talk about. So uh, we are going to talk about graphs of equation like r is equal to some number plus some other number times sine or cosine of theta, depending on what numbers you have. And if you have sine or cosine, you are going to get one of a variety of shapes. You notice this strange inner loop inside of this curve. That's perhaps the reason they likened it to a snail, that it looks like the shell of a snail, sort of. Let me just go back up here. Here's some snails. You might find them in your garden. So if you go through this half of turn here, it kind of looks like the curve that we are looking at. So we have these shapes to study. There are 8 of them, depending on what numbers you have and if you have sine or cosine. Let's go learn a little bit about the history of this thing and where does it come from and why are we interested and so on and so forth. So history of this goes back to Albrecht Dürer. Is a German painter, woodworker, who has a book on geometry of all things, and he talks about curves of this type. Next comes Etienne Pascal, 16th and 17th century. He is father of a famous figure by name of Blaise Pascal, who was a French scientist and theologian. They also have contributions to this topic. Well, where does this curve show up? Why do we care about it? Some applications I've listed here. Caustics. These are some light patterns that create curves like what we are studying. Gears. I'm going to explain that. Where does that come from? Spirograph. This is a toy that you might have played with as a kid. Let's go ahead and take a look at these things. What's a caustic? Caustic, you see here, where perhaps there's a wedding ring or something. It's a shiny cylinder. We're shining light from some direction, and light gets reflected multiple times by this shiny surface. The reflection creates a pattern that looks like a case of Limacon. In fact, it looks like the cardioid that we have in the list of curves we are going to look at. Well, if you're not married and you don't have a wedding ring and you want to know, well, where else do I see this thing? Just get a coffee cup, empty coffee cup, and shine some light into it. And just move it around. At the bottom of the cup, you're going to see something looking like that cardioid. Again, is one of the figures we are going to look at. We said has some application to gears, and well, one application of gears is in this toy Spirograph. More than likely you played with something like this as a kid. So you put these are 2 circles, and you're putting one inside the other one and kind of hold it to the side and move it around, and you make these interesting patterns like the ones you see here, a bit more complicated than the Limacon that we are looking at, but they fall into the same general category. They all fall into a category of curves that are called roulettes. Roulettes are curves that you obtain by rolling one shape around some other shape. Now, there could be any kind of a shape. Most often you're using circles because they roll around so easily. But in fact, if you're ambitious, you can roll other things, ellipses, parabolas, and so on. They have all been studied. So if you search for the word roulettes on Wikipedia, You see several dozen shapes that are named and studied. Let me take you to a quick tour of some of these things. Limacon, we said, well, Limacon, if you take a circle, put it outside of another circle and roll it around and keep the two circles in contact, and the two circles are of the same size, you get when you're tracking a curve, a point on the rolling circle, you're going to get a Limacon under certain conditions. So a curve rolling on another curve. Let's take a look at another example of this one. This is what the two circles are not of the same size, and we can get more intricate patterns, somewhat looking like the rosettes that we are going to look at later on. So a curve rolling around another curve. Here is something you can play with. Here is, let me see, where do we play with this thing? Animate. So this is one circle rolling inside another circle. This is in the spirit of that game they call the Spirograph. So if you play with this thing, you are going to be putting your pencil in that hole, the one that we are tracking here, and make the circle, inner circle, roll inside the outer circle. And doing that, you're going to get interesting pictures depending on let's increase the speed here. So here's what I'm getting. Now let me stop this and clear the trace. Play it again. So when does the path close, when doesn't? Mathematical question. When you're doing the design, probably you don't want them to close on top of each other too fast. Rather you want this to continue. So you get a picture looking like that. So that is one presentation. We said it's not necessary to always have a circle. Here is a parabola rolling on top of another parabola. Harder to visualize, but that's a possibility. Here's another example. Somebody's trying to explain what's the connection between these curves and those patterns we call caustics. When you have light reflecting from inside of a cylinder, you see this kind of a pattern forming. So here's a source of light, shining some light inside this cylinder, and it bounces back. We can use geometry to show that the first reflection always stays tangent to a cardioid, and that's the pattern we see in those reflections. So here he has drawn many different rays and drawn the first reflection of each ray, and to show that they all pile up on top of this. Okay, here's another thing for me to show you. So we are said example of Limacon is a number plus another number times sine or cosine of theta. So in this page we see just the number plus 1 times cosine theta, and he's showing you what happens if we change this number. So for sake of simple comparison, coefficient of cosine is kept at 1, and we are changing the other number. When this number is 2 or larger, we get something called a convex Limacon. If it is less than 2, it starts to form a dimple here. It's called the dimpled Limacon. If these two coefficients are the same, like 1 and 1, you get the case of a cardioid. So you have a cardioid. We saw it in those reflection patterns. If this number becomes less than this number, so it's a 0.5 and that one is 1, we start seeing the formation of a so-called inner loop. So we are going to have an inner loop. As we go around this curve, we come into this inner loop and then go out of it. If this number shrinks towards 0, so in this case you see 0 plus cosine theta, the additional number is reduced to 0. What happens is that this inner loop becomes bigger and bigger, gradually becomes the size of the outer loop. So this r equal cosine of theta, this is really two circles on top of each other. That's a moment that when this inner loop has become as big as the big outer loop, and you have in fact going around the circle twice. Okay, so that's a general introduction to Limacon, what we are talking about and what it is used for and so on. So we gave a general introduction. Special cases, we said sometimes they are looped, sometimes they form a cardioid, sometimes they are dimpled, and if you remove that dimple you get something called a convex. The shape that doesn't have a dimple on it is called a convex Limacon. Okay, let's go back to mathematical side of all of this, see what's going on. You remember the last lecture we looked at r is equal to some number times sine or cosine of theta, and we had this four configuration we talked about. We talked about how to get the equation in Cartesian coordinate. We also explained how to draw it carefully with the use of polar graph. Now we are going to graduate and go one level up, meaning we are going to add a number to this right hand side of this equation. Now the way it is written in your textbook or your software, the number that's added is called A, and the number in front of cosine is called B. It doesn't matter however you want to label them. So if you have a number plus another number times cosine of theta, and these two numbers are both positive, you'll have one of these four configurations depending on the relationship between A and B. If A is less than B, we have a Limacon with an inner loop. If A is equal to B, we are going to have a cardioid. That loop shrinks to just a point. If A is between B and 2B, then we are going to have a small dimple here. It's called dimpled Limacon. If the number A becomes larger than 2B, then we are going to have a convex Limacon. Convex, simply it means it doesn't have an indentation in it, it doesn't have a dimple in it. Mathematically, it means if a shape is convex, it means if you connect 2 points of it, then the entire line segment between those 2 points sits inside the region you're looking at. So there's a definition for the convex region. It's a very important definition. But right now, simple way of describing it is this thing doesn't have a dimple. If I have A minus B cosine theta as opposed to A plus B cosine theta, we say the orientation has changed. It flips across. Instead of going toward the positive x-axis, it opens toward the negative x-axis, or however you want to remember that. This cardioid, you notice it flips over. The dimple, it was on the left, now it's on the right. And for the case of a convex one, this flat looking side, instead of being on the left, it's kind of on the right. Of course, if you take A to be very large, what you get is a circle. That's what's going to come out. So this is the case of cosine. Case of sine, it just go in the vertical direction, just the same way. You remember with circles we had the same business. Let's go back to the circle. Cosine, we are going on the horizontal axis, left to right. Sine, we are going in the vertical direction, y-axis. In same business here. So you see, a plus b sine theta. This orientation is opening toward north, and this is the case with the inner loop. This is when a and b are equal. You have a cardioid. A between b and 2b is a dimpled Limacon in vertical direction, and this is the convex case with the flat side being in the bottom. If you have a minus b sine theta, the picture flips. So the loop here was in the positive side. Now the loop is on the negative side, and so on. Now let's go ahead and actually graph one of these things. You can graph them by having these. How many pictures do we have here? We have 16 pictures. So you can draw them and try to answer questions quickly by comparing to one of these cases, or you can sit down and do it patiently until you get the picture showing itself. What do I mean by that? Let's go ahead and go to this page. Okay, this is a typical exercise in this section. It says graph a polar equation. Case of 2 plus 2 sine theta. So I have here 2 plus 2 sine theta. Do you remember of those 16 cases? Which one is this? Well, first of all, it is a sine. So it is in the y direction. Next question is it northerly direction or is it southerly direction? Yeah. Again, as I said, you can do this thing by point inspection until the picture reveals itself to you, or you can do by matching with the pictures that we have. Let's try to do first with point by point matching. So what does that mean? So here I'm going to go to do point plotting. So I'm going to do patient point plotting. Let's plot point at a time. It says, what point do you want to plot? Let's start at 0. Well, sine of 0 is of course 0, and r is going to become 2. So r is equal to 2. Theta is equal to 0. At angle 0, we have a point. Now let's do another one. Now we are going to pick our angles to be the famous angles, so that first of all we can do it quickly, and also we recognize what the answers are. So the second case, I'm going to make this one to be pi. So I'm going to go to pi over 6. Pi over 6, and then of course at pi over 6, sine of theta is a half, times 2 is a 1, plus 2 is a 3. Somehow I missed my first point. Let me double check this thing. Remember, theta was 0 and this one was 2. I forgot to say, okay, for some reason we missed that point. Okay, pi over 4, I have pi over 4. Sine of pi over 4 is of course radical 2 over 2 times 2 is just radical 2. Now I'm adding a 2 to it, is 2 plus and then square root of 2. Notice that we shouldn't use decimal approximation. It says don't do that, give exact value. So we have that point. Next point, we are going to pi third. So little by little we find points. Pi third, and this is of course pi third, sine of that radical 3 over 2 times 2 is radical 3. So I have 2 plus and then radical 3. I have that one. Next one, we are going to go to pi over 2. So pi over 2, sine of pi over 2 is of course 1. So the whole thing boils up to 4. So I have 4 here. So that's now let's go to a bigger angle, 2 pi over 3. So I have 2 pi third. Sine of that is going to be radical 3 over 2. Again, we'll have 2 plus just what we had a moment ago, 2 plus radical 3. This is the issue of symmetry we are going to see later on. You see right and left are the same. Later on we're going to talk about that this picture is symmetric with respect to y-axis. Okay, next point, we are going to have 3 pi over 4, and that's going to be again 2 plus, and this is radical 2, so that's, we have that one. Next point, I have pi, let's see, can I type pi? No, I have to pick the pi here. Pi, excuse me, 5 pi 6. So we give the angle, and r turns out to be 5 pi 6. The sine of that is 1/2, and then we get the radius of 3. Plot the next point. Here, of course, I have pi. Sine of pi is 0, so my radius is 2. So by now, we have gone through an angle of pi. You see the crown of this thing. So next, we are going to come at 7 pi 6. So 7 pi 6. Sine of that is minus 1/2. Minus 1/2 times this becomes minus 1, and 2, I get a 1. So here, you see, the radius shrank from 2 to 1. I'm going toward the origin. Plot that point, and then continue. 5 pi over 4. That's going to be 2. Now we are subtracting everything. 2 minus radical 2. So you see a crowding here. That's like the tip of that cardioid. Next, we are going to have 4 pi third. 4 pi third. And sine of that is going to be minus radical 3 over 2. So I'll have 2 minus radical 3. You see that the points are piling up. Then I'll have a 3 pi over 2. 3 pi over 2. You can put the 3 left or right. Sine of that is minus 1 times 2 becomes minus 2, plus a 2 makes it 0. So we are making it toward the to origin. We are at the origin right now, and then we continue. So I'll have now this is 5 pi third, and then I have here 2 minus square root of 3, and then next one is going to be 7 pi over 4, and that is 2 minus radical 2, and then finally I'll have 11 pi 6, that's like minus pi 6, and that's going to be 1 okay, we did as much as our patience allowed. Of course, we could have done for every theta. We can see the picture is forming from here, going well, starting at 0. It was here. We're going around. By pi, we arrived at this point on the left side. From pi to 2 pi, we came to this crowded section at the tip of the this shape. Now, among the shapes that we had, this is called the cardioid. Now, it's giving you some options here. Do you think it's a spiral? Do you think it is a limacon with a loop? Do you think it's a limacon without a loop? Or is it just a cardioid? Do you think it's something else we are going to study later on? Something else we're going to study later on? Well, this is, we said it's a cardioid. Is that right? It's a cardioid. Now, cardioid, we have to, it says choose orientation. So what orientations do we have? Here, the 4 orientations to choose from. So of course this one. So that's our orientation. Next, we are going to choose 2 points. So this is one end of it, that the high end of it, and then at the low end of it. So we fix it with 2 points, the high point and then the low point of it, and that is our limacon. In this case, it was a cardioid. Now let's check and hope that we are right. Okay, hopefully. Now, in the same fashion, you go ahead and graph the cases with cosine, the cases with different kind of numbers here. Remember that if you want to draw something with a loop, then you have to use, if it has an inner loop, this is the picture or the icon you use for matching. If it doesn't have inner loop, it's going to be the so-called convex case, or the it's going to be a cardioid. Okay, so the picture now is one of these two. We don't have a spirals yet. We didn't study lemniscates yet. We didn't study the roses yet. If you want to do it quickly, then instead of point plotting, you can just match one of these two to your picture, and then you'll be done quicker. Here's another example, 3 plus 2 sine theta. This time let's go ahead and try to do it by matching, curve matching. So 3 and 2, this implies to us that we are going to have a dimpled limacon. Let me show you in the list that we had here. So we have 3 and 2 with sine. So 3 plus 2, in this case, A is 3, B is 2. So of course 3 is bigger than 2, but 3 is less than 4. That means our shape is going to be a vertical limacon, which is dimpled. It's a dimpled limacon. And it's going in the vertical direction with the dimple in the south side. So let's go ahead and see if we can get this thing. So it's a dimpled, so it doesn't have a loop, it's dimpled, so okay, it's a dimple. It's going to be vertical direction. What's the top of it? Top of it, at sine of theta equal to pi over 2, 3 plus 2 is going to be 5. So I'm going to go where the 5 is. So this, it looks like the 5 is here. So I choose a point here. And then when theta is 3 pi over 2, sine of it is minus 1, 3 minus 2 becomes 1. So my other point is going to be at 1. So somehow I lost my, let me erase this thing and start all over again. So it's a vertical direction. The top of it is at 5, so this is the circle 5, You notice this is 5 here, so we are going and clicking one point here. Okay. The second point is going to be at 1. So is this 1? It's hard to see. Looks like this is 1. Okay. So I fixed the lower point at 1. Why? Because when theta is 3 pi over 2, double of that is 2 sine of 3 pi over 2 is going to be minus 2 plus 3 makes it 1. So I have to be at the 1. So here I'm at 1. And the upper end, 3 plus 2 is 5. And then we are all done instead of doing point by point. And let's see if you're right. Okay. So you do it the same way. And you'll be all set. So until next time, good luck and God bless.